So we talk about, we are still like talking about CNN, so a little bit slow, but it's kind of okay. So we look into like a couple of different architectures, like the old, really old one by LeCun, the Roulette 5, and then like we talk about AlexNet a little bit, like this AlexNet like by Hinton and his student, and also like ZFLAT is more or less the same as not many people using it anymore, but historically they kind of won the kind of ImageNet in 2013, and then like VGGNet is still pretty popular somehow, and they won the competition in. Well, actually they didn't win, but they kind of like somehow is up. For some reason, it's easy to play with because it's like still a kind of old school architecture. Like people like to use that and change from there. We talk about this VGGNet a bit, and then we say like, okay, we'll talk about GoogleNet and also ResNet today, probably even more. And so GoogleNet, of course, is by Google, and we saw actually the image-like competition winner in 2014. And like for basically, if you remember that, like I think for VGGNet, they kind of like not I shouldn't say introduced, but they popularized kind of the idea of like using small filter. And GoogleNet, they have another idea that introduced a new idea that they call inception module. So basically, it's like since you're getting more and more hyperparameters. For example, like when you generate the lateral, it's not clear at the beginning whether it's good to use what kind of filters. So the idea at that time is like, okay, why don't we use like multiples? So we try like different filters and then just let the lateral to train on that to select the filter for us. So therefore, like it will be like architecture like that. The live implementation will be like this, right? And you have this. For example, I can have 1x1 filter, a 3x3 filter, like 5x5. I can also use a mesh pooling there. So kind of like let the lateral to design and let it to train it. But this kind of live implementation is not efficient because like you have, if you count the number of like operational parameters. So I have 1x1, 128 filters, then I will have the size, let's say at my input, let's say 28 by 28 by 256. Then if I have 1x1 filter, 128, I have like so many number of coefficients at the output. And I look at like also 3x3, let's say 3x3 have 192, I have also that, and then I have like basically 28 by 28 by 192, so many of them, coefficients. And then if I have 96, I have this, and then if I get 3x3 polling, then I don't do any reduction in the size, right? So therefore I still have like the same. Okay, yeah. In this polling, like basically it used like the stripes one. It didn't do any downsampling. So therefore you see the size is also 28 by 28. Actually, it doesn't do any downsampling because if you see that like they do this here, like each of this block here, the output has the same size. It's all 28 by 28. So you can just simply stack them all together, right? So therefore it becomes like 28 by 28. But the input thickness now it goes from like 256 kind of channels, I should say maybe, to like 672 channels. So this is a little bit too big in terms of like computational capacity. So one way we can do it is like we just use the one kind of like small filter idea, basically the 1x1. Actually, yeah, one-by-one filter. I think like we talked about that like, earlier. I forgot where, but basically the one-by-one filter is trying to just to compress the layer. Right? One-by-one in the sense like you have a filter, like for example, like this is a kind of like a flat there is like a filter, and you just do this with a kind of a Hardeman product. It's basically it's like element-wise product, and to get a value. Right? Yeah, sorry, actually, I just basically do a dot product to get a value. Right? Then I have like multiple filters of that. Then I get like, let's say if I have 32 filters, then I have a new thickness of 32. So in this case, I basically have a compression, right? Using this one-by-one filter, compress from setting kind of like 64 channels to 32 channels. So we can use this in this kind of like so-called inception module, right? So what we can do is like instead of like go directly with the input with I forgot how many channels, like 256 channel, we can first compress it before we're going into this 3x3 comb filter. So, and this is a sometimes called this bottleneck layer. And then this one-by-one bottleneck layer, for example, here I have from 256 compressed to like first 64 channel, and then go to this 3x3 comb filter. So the output size will be, let's see, is that the same here? 192, 192. The output size is the same, right? But the number of operations you can count it will be much smaller because I first compress the input here before I go into this comb filter. So I'm not going to count it. You can just go back to the slide and count it, but it's like quite simple, like arithmetic. And like you can do the same thing for other block, right? So for 5x5, you also first compress that. And for the polling operation, you can also compress it after the polling. So so doing this will kind of like decrease the thickness at the output, right? So originally, if because the polling you don't do you only do strike 1, so initially there's no compression in that output of the polling, right? So if like you start with 256, you still have 256. So therefore, like the kind of the whenever you add the polling without this one-by-one filter here, you always get the output will be larger, right? More thicker, right? But now if you can shrink this like mesh polling layer with less number of channels, kind of it's possible. Like of course, in this case, we still get it bigger. But if we use less filter for other kind of blocks, we can actually can maintain the number of channels like for this GoogleNet like what's that called? Inception module. And that's basically it. So therefore, we just have this inception module just plug in like all over the network, and this from the so-called GoogleNet. And it's actually quite simple stuff. And and they stack many layers there, and they also play another trick to trying to train this network, is trying to have an output in the middle of the layer in the network. So this is more or less like have the same expected output. Like so, basically you have like originally you are training end to end, right? But basically you also put copy your like ground truth in the middle like of the network. So when you train it, you basically you also have some information to get back pop like this way, rather than like it's pretty far from like very end. So this helped the training a little bit. And actually this idea is kind of like you can see when the network become deeper and deeper, we need to come up with new idea, just trying to kind of train the network efficiently. Because like if you use the plain vanilla neural network with like 100 layers, even though you put in the tricks we talk about like rate initialization or like batch normalization and so on and so forth, or like dropout stuff like that, it's still not sufficient to propagate this gradient back all the way. So because sooner or later your gradient will just vanish, right, inside the network. So you just need to find ways to have this gradient pass back effectively. So you see GoogleNet use this trick here. ResNet have a different trick I will talk about. And that's basically GoogleNet. Yeah, as I mentioned, they have basically, this is the classifier output, right? But you also put the output somewhere here for it to train. So and so therefore it can help to train a little bit. And that's the performance. Okay, that's and some summary note of this network. It have 22 layers, and have lots of this inception module there. And it doesn't use a fully connected layer. So at the very end, I believe. And it actually has less number of parameters than AlexNet, even though it's deeper. And as I mentioned, it won the 2014 ImageNet competition. And so finally, let's talk about ResNet. That is in 2015. This is one of the years you can see the depth really go I shouldn't say exponentially, it's by a huge margin. Basically, the number of layers earlier is 8, 8, and 19, 22, and then this 2015 just go into 150. And ResNet is by Microsoft Asia Research, I believe, and they basically break all the won all the competition. Won all the categories of the ImageNet competition in 2015. And so the idea is they have this really, really big network, really, really deep network. As I mentioned, when you get that deep, it's really difficult to train, right? So the idea is like that. I guess at least the original idea is if you have the network is getting, you assume that when you train pretty well in the early layer, maybe the early layers of the network, since it's already trained pretty well, so we expect that when we add a new layer there, then we are essentially just refining the existing input, right? Existing whatever intermediate output, I should say. So therefore, this part of the network, rather than training creating the brand new output there, we're essentially trying to just train the difference from the input and the output. So it's we're trying to create a network to just learn to build a residual of the input there. So therefore, they call it residual network. That is the original idea, I guess. So, but it turns out, I guess, why it's working so well, most likely is because of this link bypass. You see, they always bypass a couple layers there, right? And whenever you have this bypass link here, you think of backpop. When you backpropagate the gradient, you can just ignore this layer here, directly fit this backpropagation, gradient information, pass through this layer. So therefore, at least some of this gradient information can go pretty quickly and all the way to the end. So that's why it allows you to train the earlier layer easier than if without this, sometimes people call it this super highway or whatever. And I'm actually later paper, they also mentioned okay, they ignore this residual kind of stuff, but they just trying to add this kind of links to bypass certain layers, and also train pretty well. So therefore, ResNet, I guess the main contribution in that year is to introduce this superhighway, and that allows you to train much thicker layers. Deeper network, and of course they in that paper they also make very kind of good analysis there they motivate why they should do that. Like they first look into, okay, if I have like 20 layers, and then I just have a vanilla like old school neural network, and I could increase the number of layers. So of course, like when you increase the number of layers, like at the beginning, it tends to like decrease the training error and the testing error, right? But as he shows, like the author shows in the paper, that when they increase the layer up to a certain point, let's say from 20 layer to like 56 layer, there's no longer any gain. Actually, it's even getting worse. The error rate actually goes up. And this is not just the error rate for the testing error. So if you're saying like the testing error goes up, it's okay, because that just means can be like you overfit the model, right? But the problem here is that even the training errors goes up. It means that you can't even train the network there. So that motivates what they did, as I discussed earlier. And so as we mentioned, this basically have this kind of, they, at the beginning, how did they call it? I forgot. A residual mapping, something like. But if you think of that, it's basically just like some superhighway link, I guess. And that's basically it. For ResNet also, it's actually pretty simple. And if you look at the other stuff, it's pretty standard. Like of course they stack off this residual block. Residual block is basically just a block with this superhighway that kind of hop through some of these layers, and they use a small filter as we expect, and so periodically they kind of double the thickness of the filter, and also they kind of also do a stripe through kind of downsampling. And so they don't actually use a mass polling, or like they don't use a polling directly, but they just use a filter, but they use a stripe tool that effectively have the same downsampling effect as like doing mass polling. And they have a conf layer at the beginning. And also like they do not use lots of fully connected layers. Actually, we mentioned earlier, right, fully connected layer tends to have lots of parameters, and that's people are getting not. I guess at least the trend is like people are trying to avoid fully connected layer if possible. They still use some fully connected layer. Actually, I forgot to mention, for GoogleNet, actually they didn't use fully connected layer. They just use a FH polling there. So you have the final layer, you just FH out part of the result, then that will be your outcome there. And then you just actually maybe I just go to the slides there. GoogleNet. Yeah, they didn't have the fully connected layer. I don't have a slide with that. But anyway, so you have, so basically you just FH out, and then that is your output, and then you use that output and go for a softmax, then you can do classification, right? So just treat that value as the score. I mean, the value after FHing as the score, basically, instead of going for a fully connected layer. But as I mentioned here, ResNet is still use fully connected layer, but comparing with earlier network, for example, like AlexNet, it has multiple fully connected layers. This one only have one. And for other things, like let's see. And also, like, they have different variation for ResNet, just have like different number of depth. Like for example, like 30, like 34, like 50, 101, and the deepest one have like 152. And for like deeper ResNet, they also try to like reduce number of parameters, use the same trick as we kind of like mentioned before. This like bottleneck layers that just first have a one by one filters to make it kind of like thinner and then like go 3 by 3 and then expand again. So for example here you have start with the input is like 28 by 256, right? Then you compress that with 1 by 1 filter. Now the thickness number of channels like from 256 like down to 64, and then like here therefore your filter like only 64, right? And then you go for another 64 here, then you expand it again like with 1 by 1 filters. This kind of like reduce the parameters, number of parameters quite a bit. And also the computation. And this is other detail like about training for ResNet. They use batch normalization. I mean the paper they also like modify half-year like initialization. Like half-year initialization is by Benjo's group like in 2010. If you remember, we discussed that. And for Value, they find that like it's more efficient. You should kind of reduce. I mean with the factor of 2. If you don't remember, just go back to earlier notes. Like I guess we spent some time there. And we have used stochastic gradient descent and momentum to train that. Learning rate is 0.1. Whenever I go to plateau, it just reduce that like by 10 times. And it has a mini batch size like 256. No, did not use dropout somehow. I forgot that was weight decay last time. Actually, weight decay, by the way, is just slowly decaying the weight. And I think it's like it's kind of exponential. It's something like exponential minus k t, let's say. And this k will be this decaying factor here. So it's pretty small, so therefore it's decaying really slowly. And so as mentioned, I can train really deep lateral now. It's at 152 layers. And deeper laterals give us better result. That's what we expected, like what we like, because as mentioned in the beginning of the paper, they show that like if we do it in a naive way, it doesn't necessarily like if we increase the number of layers, we actually can kind of increase the performance. And basically, actually one thing like we like to mention also, I'm not sure it counts or not, but for classification, at least it works really well. Like it's only less than 4%, and actually it's like it's even better than human in some sense. I have some observation when I say better than human here, because I don't know like how we look into these error cases. Of course, they have some error cases. This to human is obviously wrong. Maybe I don't know, but actually people try that. People, precisely when I say people, I mean like Andre Karpathy, like when he taught like the CS241N like in Stanford, he also spent 2 weeks just trying to train himself as the human classifier for the image like competition. And that's the one. I think I mentioned that also. Like he got 5% or something, and it's actually it's worse than ResNet. Here's from one of the paper like 2 years ago, about 1.5 years ago. So this is a very nice kind of comparisons of all these architectures we just mentioned. You can see that like VGGNet is like quite popular, but in terms of performance, it's okay. It's not doing the best. Like so, this is actually the performance. So you're in the middle here, and this is like a number of operations. So it's like VGG is like just the name suggests it's very big, kind of like I forgot what's the. I think one of these V is a very like I forgot why it's called GG. So anyway, but it's lots of operations, kind of, and also like the circle size here actually indicates the memory usage. So also like it's not efficient in many aspects. Like it's not the best performing architecture, and also like it used probably is the largest install in terms of memory usage. And you look at the old school, like the earliest one, like AlexNet it has quite a lot of memory usage as well. And performance-wise, of course, after so many years, it's no longer that good, like compared with other guys, other architectures there. And if you want to pick something to use nowadays, maybe you want to pick like GoogleNet or like ResNet. So some of this inception net by Google is more or less just with this inception layer, but also like borrow some idea from ResNet with this superhighway stuff like that. So ResNet actually have a pretty good balance, right? But I guess if you want to, just in terms of classification, of course I am not sure like how this translate to other problem. So for example, like this is basically just the classification result. Right? Once you have the network, you can fine tuning some of these parameters and use that for other application as well. But of course, nowadays it's so easy to grab some of this network and retrain it yourself. I mean, like fine tune the network yourself. So you don't need to really just pick ResNet or pick instruction net. You can try all of these. And this is more of these slides here. This one in the paper also mentioned about like power consumption is pretty nice, and also like this also show the forward time for different networks there. I guess I will just let you look into that yourself. And also, like I would like to mention a couple of papers and other architectures here. And one of these network paper is well cited because it probably is the one that introduced this one-by-one conf. I mean, this bottleneck layer idea. So you go through this one-by-one filter conf layers, and then like to do a compression, and then like mix with other filter, and then maybe expand it again. So honestly, I didn't go through the entire paper. I only noticed that like usually people credit this one-by-one conflict idea back to this paper, and there's another paper. Let's see. Yeah, I mean, this is another paper by the same author of ResNet. So in the original ResNet paper, they have like each of these module, like ResNet module. I forgot like how do they call it. And the module is basically have a module that I have the name there. Let's see, what did they call it? Residual block. They call it residual block. So they have a bunch of residual block and attach them together, right? And this paper is just saying that like you don't necessarily need to pack one of these residual block one at a time. You can just have this superhighway that jump even farther away, right? And this totally makes sense, and they show that this actually gives better performance. This is kind of expected also. And another paper that look into another direction is like instead of like having more layer, maybe what we can do is just have a wider layer. So what they mean by wider layer is simply like have the number of filters increases within that layer. So for example, like this one originally have only F filters here. We expand that to like F times K, so many filters. And at least in this paper, they argue that like this actually can get you better performance. For example, they show that like for 50 layer like wide ResNet actually can outperform like 152. Like just make it like wider. And this is a further extension. Is again like by the same authors of ResNet, and they call it ResLix. And so they actually is also following the same spirit like we talk about, like make it wider and like jump farther away. And they borrowed this kind of like inception idea from Google. Actually, the two companies basically borrow ideas like from each other. Now they're saying, okay, if I have this, instead of like doing kind of like wider, actually it's more efficient, at least they came, to have these parallel pathways. So instead of like wider networks, wider layers, like with more filters as we showed earlier, we just have this parallel pathway. It's very much like inception layer, inception module, but what they show also, like you don't actually need to have like different combination of filters. You can essentially use the same kind of filters. For example, here, like all of them actually using one by one comp, and then like the 3x3 comp filters, and then one by one again like compress. All of this is basically have this bottleneck layer, just make them in parallel. And this is another paper that is in a different direction. It's regarding training. It's kind of similar to like dropout that we discussed earlier. You can introduce some randomization like during training that can be treated as like regularization. And what they do here is like they just when they training, they kind of like randomly drop out some of the block in the middle, some of this residual block, and they show that you can kind of train it better this way. And this is another architecture. This is kind of saying that like residual is not actually necessary. I mean, that is actually all this superhighway that it actually counts. So they have this called factor that is like don't care about like whether we are training residual or not, but simply you have link that jump very far from top to bottom and form kind of like a factor like structure. And then when they train it, they also use dropout. They will basically drop some of the path completely. And of course, like with testing, you will use the entire network. And this is kind of a very similar idea that you also have like connection, like kind of dense connection, like jump from input, like or like from intermediate output to very far away, and also like they show that this kind of help. So therefore, like essentially, like all this is similar idea that introduced by ResNet. Is that if you have this wire that go very far, then it's kind of apparent, right? Then when you have backpop, you can just go like fast, like from here, like all the way back, like or all the way back to here. Then you can change this comp layer parameters very quickly. Therefore, it is actually totally makes sense. And I don't know why this slide is here. Oh, actually, yeah, I put the slide in the wrong page. But anyway, so another idea is like not idea, but kind of important is the squeeze net. I already mentioned that, and I'll show you a demo. The idea is that the ledger is getting too bigger and bigger. Even though the little one, they have all this trick to make it kind of smaller, right, efficiently, right. This squeeze net is just trying to go more extreme, like they're not looking into performance, but they're looking into the size. They want to make it really small. Then you can use it in a cell phone or something. For example, like they have the model eventually compressed to only like 500K. So if you think of for example, like AlexStat or something, I forgot the exact number, but probably say around the size of 100 meg or something. So therefore, definitely this is not something for. No, you can still use it for cell phone, but like you probably cannot put many of this like network in your cell phone and stuff like that. And also like they are also not just looking into cell phone, right? Because you can also use that for FPGA and so on. And for FPGA, typically you don't have so much memory, and the limitation is even bigger. And basically, the idea is like they have again like they just borrows many of the old idea there. Like they replace this 3x3 filters by 1x1 filters. This is the ideas keep coming back as I have this one-by-one filter, and then like we also like trying to decrease the number of, they have many of these 3x3 filters now are one-by-one. And for the remaining 3x3 filters, they want to make sure the number of input channel is also small. So they kind of like, again, like every time you go to the 3x3 filters, you first do the one-by-one compression there. They have this one-by-one conf layer to compress the input. And then they also they also mentioned one first strategy. This is not about compression, but they mentioned that like now you have compressed the lateral so much, and kind of reduce the number of parameters, so on. It actually it seems that like, you will gain if you delay the downsampling. So remember, like, we always typically have a mass polling, or maybe even just FH, or like not FH polling, but mass polling, and also like just a conf layer with strike 2 to downsample the input size, right? Okay, be careful. Like there's like several confusing. Like we have input size is the input of that image, but we also have the number of layer. Let me call it number of channels there, like for that thickness of that input there. So we can change the thickness of the input, but typically we also decrease the size of the image there. Right? We typically decrease the size of the image for mass polling when we have the old school style. Or we can use just conf filter, but with different stripe, like stripe other than one. And they kind of show that like if you delay this downsampling, like later in the network, it gives you better performance. Even though of course it have kind of a trade-off with capacity. This is kind of summary of these architectures there. We mentioned like GoogleNet and ResNet, and you can see like many of these ideas just cross hybridize through, is that word, to different kind of models and architectures. And I have less than, I have less than, I don't know whether I should count 5 minutes or something. I have 5 minutes or something. I have 60 slides, or like 80 slides. But this is like all old stuff actually. But I guess it's like, so I will just fill it through very quickly. So because we mentioned many of these things, but I guess it's good to emphasize a bit. Some of these CNN tricks also occur like in general network, like we discussed earlier, right? From vanilla neural network. So actually, even for like general machine learning, right, data augmentation is always very useful. And if for images, you can have all kind of tricks to do like data augmentation. And I'll just skip that. And okay, this one I guess I should emphasize a bit more. Actually, this is like what people got very excited at the beginning of like neural networks. Right? They trained this little ELISA and did really well for image-like competition, for classification. Now they can fine-tune that model architecture a little bit. Now they can train it like for other application. And it's not something like so obvious like for models in the past. This is, I shouldn't say it's unique, but it's like pretty rare like for other machine learning model. So you can have a network like this, you have all these parameters inside the network, right? So now you have a new problem. I can just freeze all these parameters, let's say, and then just say, keep the last couple layers. I just try to train that. So it will be very simple. Right? Basically, you have this backpropagation with the error probability backpropagated gradient. And for all these layers, I basically simply ignore the gradient. I don't do any update. And for these layers, I will just do update. And that's it. That is now people call it transfer learning, right? So I guess 5-6 years earlier, like not many people talk about transfer learning, but since we have stuff like as easy as that, everyone is talking about transfer learning basically. It depends on like how many data you can have. You can also like decide like how much layers you are going to freeze, right? For example, if you have only small data set, then maybe you fit like most of the layers. But if you have like a little bit more data, then you can fit like less number of layers there. And this is the paper that they tested. Like basically, they I forgot. Like you probably need to look into the paper, but they kind of show that like, okay, you can transfer learning to other application. And yeah, this is just a generic suggestion, right? If you have basically what you're hoping for is like whether you have a particular problem. That problem can be discussed in somewhere else. Maybe like you have like for example image classification, right? Generic image classification, but then later on you have classification for medical images. So then the data will be in general not the same, right? So if your data is kind of similar, then you probably can get away with less amount of data. You can maybe like just add a simple linear classifier on top of the layer, let's say, to do the classification. But if you have like quite a lot of data, you can of course like do better. Maybe you fine tune more layers and so on. If you have like totally different data set, then and you don't have much data, then you're kind of in trouble. So that's the scenario that you probably you need to find other ways out, like whether you can get more data and so on. So I'm seeing that like someone is leaving now, so I guess I probably should stop. So anyway, like I guess I probably will come back and talk about some of these stuffs like next time. After all your presentations, I guess. Who is the first presenter? Do you guys know? Like you guys know your schedule, right?